All right. Maybe I should just go. All right, so I'm Dion Marais. I'm from South African Nuclear Energy Corporation in South Africa. I'm responsible for data acquisition, data manipulation, control systems, all the software stuff at our facility. And on top of that, I'm instrument scientist for the neutron strain scanner as well. So I wear many hats, but it's okay. I like my job. Okay, so this is a picture of a structure near Magaliesberg Mountains where the facility is. And the structure brings me to the structure of the talk, which is the introduction. I'm talking about ScanManipulator. Sorry,
Apparently it's not shared. Yeah, nice presentation. Yeah. It's shared. Okay, sorry.
Wrong information somewhere.
Always a problem of communication.
Okay. All right, so, thank you. Okay, so I'm going to talk about ScanManipulator and its functionalities, some international benchmarking that we did, and then the future neutron beamline facility that we hope will start up. Okay, so as for the introduction, everyone knows the world, but no one really, everyone doesn't always know where South Africa is. It's in the south of Africa. If you have a look at this picture, these are neutron sources around the world with scattering facilities. So you can see Necsa is there. We are there in Africa. So if you look at how South Africa looks, people who know about South Africa, you probably heard about the Kruger National Park. So that's in the northeast of the country over there. Maybe you've heard about Cape Town. We've got a nice power station over there looking out of the mountain. And then if you look at where Johannesburg and Pretoria is, close to it, we have the Necsa site in the Northwest Province. If you look closely, you'll see my house just over that hill over there. Okay, so our source, it's a Safari 1 nuclear research reactor. It's a 20 megawatt tank and pool type. She's pretty old. She's 57 years old now, but she's very well managed. So it runs about 300 days per year. We offer radiation services. We do in-core neutron activation analysis, medical isotopes, which we're actually the 4th biggest producer of Molly-99 for cancer research in the world, or cancer treatment. And then you also do neutron transmutation doping for the silicon, for silicon, for the electronic industry. Okay, so then you also have neutron beamline facilities, which is why I'm here. So we're not a very big facility. We only have 3 instruments, but it's 3 more than 0. So the first instrument, MPISI, that's where I work most of the time. It's an acronym for the Materials Probe for Internal Strain Investigations. And MPISI is also the Zulu word for hyena. If you look at where we got that name, if you look at the, if you look at the fur of hyena, it's pretty much, you can see the crystal structure on it. So we got that one. Then we have PITSI, it's the powder instrument for transition in structure investigations. And it's a zebra word for, it's a Sufi word for zebra. And you can obviously see the diffraction pattern here on the zebra. Then in Ndlovu, it's the imaging neutron device to locate the obscure and visualize the unknown. And that's elephant in Zulu, and you can just see it's because of the pure size of this thing. Now, this instrument is unfortunately not functional at the moment. We're in the upgrade stage. Okay, so this brings me to the data analysis software, ScanManipulator. Okay, so the implementation was done with Python and PyQt, using NumPy for array manipulation, PySpec for function fitting. So we use all these open source stuff that we can get to minimize the workload as well. FAN2 for artificial neural networks, H5Py to access HDF5 library, Py132 so you can directly export your data to Excel, Matplotlib for 1D, 2D, and further data display, and then Mayavi, which is a great product or library, I think, for 3D data display. So the input, we can use a subset of Nexus, HDF5 encoded, of course. You can get some results from XTAS in there, 2-column ASCII, FullProf, and some custom parameter study files we can use, and then also real-time from the DAC. And after that, you can do some array manipulation or some data manipulation, which I'll come to in the next slides. And then as output, It can go to FullProf, GSAS, ASCII, of course, Microsoft Excel, and all the graphs can go to text or BMP or whatever the backend provides you with. Okay, so how manipulation works. First off, you start with your detector frames. It comes in here. Okay. Get the frames from the detector. Then you can do a lot of stuff with it. You can add parameters or add parameter-dependent rotational axis. You can remove data points below some threshold. Sorry, let me just quickly do this. Yeah. Okay, so you can remove some data points below a threshold. You can reduce the data sets by periodic removal. You can rebin, transpose, combine data files. After that, you can do flat field correction, geometric correction. Then there's some new stuff that we've added for neutron attenuation. You can integrate, normalize, crop, and then stitch all these together to get your nice diffraction pattern. Okay, so one of the things that I mentioned now is the neutron attenuation correction. So if you have a beam coming in, going onto your sample and exiting the sample through a detector, you can see these path lengths vary according to your angle and the position in your sample. Now, to correct for that, there was some implementation done in ScanManipulator. You physically put the dimensions of your sample. Thus, you grid the gauge volume up in some grid. The more points, the better it is. Obviously, the longer it takes, though. And then it will calculate all these path lengths, and it can distribute your attenuation correction according to your angle. So if you have a look at the sample or the example over here, this is high density polyethylene. We all know this scatters isotropically, so on your detector you essentially should get everywhere in the detector should be the same, but it's not in reality the truth, because if you go according to your diffraction angle, you'll see as the diffraction angle increases, your intensity increases. And that essentially is because your path length actually is shorter on the higher side. So this thing can go and calculate some attenuation correction coefficient. And then if you multiply these together, you get this nice isotropic scattering out. Now, where this is important, if you do position-dependent diffraction studies, for instance, what we had here, we had some steel sample, which was rolled, and now we wanted to see the different phases in different parts of the material. So we had a small beam, 0.3 millimeter beam, scanning through it. And you can see the diffraction pattern that you get out here. But if you look at the attenuation correction coefficient and you apply that to it, you get different phases between uncorrected and the corrected data. So this is very important if you want to do precise analysis of your samples. Okay, something that I've been working on, which is not quite finished yet, that's why the slide is so sparsely populated, is 3D attenuation correction. Now this works, but the way I've done it is very slow. Because for each pixel, you essentially need to go in 3D to your whole detector, and for each point, it just gets a lot of data. So this is something that is still in the process of just getting a bit faster, but this is coming up. Okay, so something it does as well is function fitting. This is what lots of software does. Essentially, we can do pseudo Voight, and then there's also entry curves, reflection transmission, Z scans, wall scans, so you can fit all of these easily. Another thing that it does, it's optimization for counting time. So usually in experiment, you will have some fixed measurement positions. Now this is specifically for a strain experiment. You'll have specific measurement positions and you count according to a fixed time. After the time is done, you move to the next position, you do the data acquisition. After the time is reached, you go on. If you have more positions, you go on. Afterwards, you do peak fitting and data analysis. So as a conventional way, what we did here is you specify only a maximum measurement time, your peak fit criteria, and then sample position. So when you start moving, as the data is acquired, it will do automatically the peak fitting. And if the fit criteria is reached, it will move on. Otherwise, if the max time is reached, it will move on. If there's more positions, it will do that. And then you'll get to all your positions and all your peak fitting that is done at the end as well. So example for this, we had some steel sample that was welded over here. You can see the weld color over here, so the material is thicker on certain parts. So if you go and you do a normal time-based acquisition, you can see the peak intensity is very high at the surface of the sample. And as you go deeper in, as your path length increases, this intensity will drop off. But if you now do it with your statistics-based acquisition, you can see you've got a nice flat intensity profile. So what you can also see here, as you go deeper into the material, usually your time-based, all the times will be the same, something that you set up. But if you do it this manner, you'll near the surface, you will count less, deeper you will count longer. Easy as that. And also here you can see, because you have now the set statistical measurement parameter that you have, that statistical based error is much more flat in your normal acquisition method. Okay, this was a proof of concept only. We have not really implemented it in any experiments, but it's a nice thing to think about. So this is where you have do sample positioning using artificial neural networks. So the idea was to have these fiducial markers on a sample, same as essentially what you would have done. I don't know if you know this ScanManipulator software for strain scanning, where you have a 3D coordinate positioning machine, and you have a sample, and you sort of touch probe your sample, and you put it on an instrument, and you go on with the experiment. But you don't have a touch probe, so we thought maybe let's do something interesting. So we created these fiducial markers using different materials. So the idea is to have one measurement on the sort of in the center of the material, and then using artificial neural networks to locate that fiducial marker. So if you look at these materials, alpha ferrite, gamma ferrite, and beryllium, they've all got diffraction peaks close to 90 degrees, but separated. So you can very nicely integrate them. So what you see here is, if you looking at the diffraction angle and measurement number, now these measurement numbers are just around the center, you have different intensities of these different materials. So you can then basically take this, divide it up. You can have X and Y and Z positions with intensities for each material. And you can take this and put it into cascade architecture at artificial neural network to train it. And then we did a test set as well, and we can see all the results that we got back was within the 3 sigma limits. So it sort of worked. We've never really used it after proof of concept. It's a data visualization. You've already now seen the 1 and 2D graphs that you can plot. You can also do polar plotting. This is useful for if you do texture analysis. There's a lot of parameters you can change here. You can add some patches. You can make your graphs look very nice in publication ready quite easily. And then 3D visualization as well. This is through that Mayavi library. So you can have lines, surfaces, 3D volumes, and cut planes. You can make very nice pictures using this. Okay, as for international benchmarking, this was done under the Brightness 2 project, which is standing for bringing together the neutron ecosystem for sustainable science with ESS. Very long way. Okay, so this was under work package 2, strategy to deliver neutrons for Europe and beyond. So this was a collaboration between ILL with the SALSA instrument, Engine X instrument at ISIS, Stress Spec at MLZ, and then our instrument at Necsa. So this was just for strain analysis software. So the deliverables under work package 2.1 was to set up a calibration protocol for all strain scanning instruments and definition criteria for a neutron quality label. And then objective 3, I'm going to read this out, is to benchmark the accuracy and reliability of results of the participating neutron strain scanners through calibration measurements and analysis methods, including the benchmarking of the positional accuracy and data analysis software. That's where this comes in now. The software we compared, software called Align from Vladimir Lucen from ANSTO, FITSI strain was Thilo Perning from ILL, and then ScanManipulator. So the outputs of this deliverable were the Brightness 2 report, There's a publication on this, and then we also established this neutron quality label. So how this comparison worked. So it's basically a comparison between, it's a combination between the instrument as well as the software. You couldn't really separate it out because it looked at both aspects. So first off was to quantify the reference position of the instrument. So we had some specific samples made up to do this, and then use the different analysis software to do the calculations. Okay. So there was also a 5-hole sample, and then a circular sample as well. So obviously I'm not going to go through all of this, but what comes out of it, the software instruments were compatible with all flat surfaces, but the models for curved surfaces were only implemented in fit stereo strain, so the rest still needs to be updated with these models. Okay, so the future beamline facility, beamline center. We are looking to build, like I said, our reactor is very old now, so we need to replace this instrument, or this reactor, and this will be with a new multi-purpose reactor with lots of different sources, like a cold neutron source, fast, hot, and gamma source, hopefully. And then beam delivery systems with a whole new beamline center comprising of a reactor beam hall and a neutron guide hall, fuel material testing facility, fuel and target plate and fabrication facility. And we also want to expand the isotope production and the radioanalytical capabilities. And then obviously also we need to upgrade our on-site accommodation for external users. So this is just the timeline. So we started with the pre-feasibility has been done. Feasibility study has been started as well. So we're now entering the concept design phase, and this will hopefully we will start construction in March 2025. So the instrument selection, this is a big wish list we have. Don't know what's depending on the funding what we're going to get out. We've had some stakeholder engagements already started. There was again a brightness project which we used to bring up this publication, which is a landscape and future direction for neutron scattering in South Africa. We will also be hosting a stakeholder engagement session in November. And then we've got the IAEA IRUR mission to help us with defining the scope as well. So what does it mean for software? We need a complete new suite. So that means user office, instrument control software, user interface, data reduction and analysis. So proposals for collaboration is open. So if you have something, please contact me. Thank you very much. That's the end of my talk.
Thank you very much, Neil. Are there any questions? I think we can have time for 1 or 2 questions. Yes.
I understand your change in the data taking process correctly. You moved from a process where the user takes as much data as they think they need to a process which informs the user that they actually already have enough data.
Exactly that is. So it saves a lot of time. Yep.
Did you have any problems getting the users on board with that? Because you're basically now telling them I tell you when stop data.
Well, the user usually knows how good his data he wants. They usually know they want to go for 50 microstrain. So normally we've got like an offline tool that you calculate, you need to count about this long. But if you've got a sample that you move deeper into the material, that will have to change for every point. So this just automates that essentially.
I think you have the right metrics exposed that it's very visible for the users. Okay, you've got the resolution or whatever.
It's basically one parameter because they know where they want to measure, they know what quality they want, because usually for stress measurements you have you've done some simulation or you know how much stress in the material, so you just want to measure better than your trend, so you know you're actually measuring correct stuff, you're getting correct data out, so they usually know what they want. It just helps with acquisition.
Okay, thanks. It's very relevant for us as well. 1 minute longer measurement of expo can result in 120 gigabytes of more data.
Yeah.
And convincing users that they have enough is not so easy always.
Okay. So let's thank Deon again.
Thank you
very much.